Welcome back, everybody. Yeah, up here. Okay. So just want to give a quick look at looking ahead at this near future in the schedules for what we're going to start the class with. So we've given kind of the introductory lecture, what to expect this semester, what we're going to be talking about. And the way the course will start is, you can see we've got the first six lectures, or six or so lectures here on the schedule. And this is all the next six the classes are going to be following the Riemann geometry notes. If you click on that link, there's the PDF notes for what we're talking about. And you'll probably be able to tell that this is all math. So what we're doing here is, as you can see on the schedule, is topology. Then we're going to talk about manifolds. And then we're going to talk about Riemann geometry, which is sort of metric or distance geometry on manifolds. And that will be sort of the mathematical or the theory component of what we need to know in this class. But none of these topics are really about machine learning, at least yet. So you'll have to bear with us while we cover math, seemingly very abstract topics, but keep in mind as we're doing this to keep us grounded in the real goal of the class, which is analyzing data. Keep this picture in mind, maybe, as we talked about in the introductory lecture, this manifold hypothesis that when we have data such as images or any other type of real data, represented typically as just a list of numbers you can think of as a vector, a Euclidean space vector, that the real data that we're interested in lies in a lower dimensional manifold, smooth hypersurface, if you will, sort of embedded in that extrinsic representation of our data. And so this is why we're going to be doing six lectures, 3 weeks worth of just math, is to understand the sort of principles behind these manifold objects that we at least assume our data live on. So let's keep that in mind as we do lots and lots of math, is the point. The other thing I like to say is that each of these sort of subsections here, topology, manifolds, and Riemann geometry, are an entire sub-branch of mathematics in and of themselves. And so you could spend a semester or more on each of these 3 topics. And of course, we can't spend that much time on these topics that they really deserve that much time. But the goal here is not to make you all experts in manifold mathematics, but rather to get a somewhat a foundation of the basic rigor of the mathematics, yes, but also more importantly to have a good intuition of what these what the topics and issues are, especially as we start to think about our data in these high dimensional manifolds. Okay, so that's what to look forward to. Any questions there on just the next thing to point out is that homework 1 is posted here today, and it's due in 2.5 weeks, I guess that is, on the 12th of September. And it'll be electronic through Canvas. I'll make a place you can turn it in there. Maybe we can take a quick look at it. This is there's some instructions here, but it's basically what we covered in the policies. Maybe I'll just reiterate this second part here. Well, basically, this first part in bold, that is to give, some enough explanation of your answers, not just to give a final answer. Like if, it's a question, but that the answer is a number, don't just give us the number, like how did you get the number, that kind of thing. And everything's been done in a Jupyter notebook. includes written answers, mathematical derivations, and also some Python coding, all in the same document. Yes, I did want to repeat just that. Remember the policy, it's in the policies we covered last time, is that you can work together, you can discuss topics and questions with each other, but and you can also look on the web for hints and extra reading about different topics or tips on Python programming, et cetera, including the use of AI like ChatGPT and those types of things. But the bottom line is that at the end, the final product should be your own. You should write it up on your own. Don't copy it from internet sources, ChatGPT, other students, but rather write it up yourself. And finally, remember to cite any sources you use, whether they be just a web page, Wikipedia, ChatGPT. And if it is an AI chatbot, please tell us what prompts you used in that. Just as a sort of warning, I did ChatGPT and asked ChatGPT to do the homework for me. And I will just say that it gave some questionable results. So be careful, be forewarned how you use it. That should always be the case. Be careful not to believe ChatGPT always. Okay, so just really quickly, I won't go through all the questions from anything, but just to say, you'll notice that questions number 1 and 2 are pure like math problems. They're topology problems. And it's really asking for an argument about topology, and the questions here are really, it gives an argument. You might even call it a proof in the first 2 parts. So there'll be some math, very abstract kind of problems here. And then you'll see in part 3 and 4 that we're asking for Python code to do some things. Again, not really data analysis as of yet, really still doing math type things, but doing some experiments in Python. The first one is to look at the stereographic projection and how you form a sphere from a representation, a 2D representation called the stereographic projection, and do some plots of that. And number 4 is going to be looking at this weird behavior of random data, or not, I shouldn't call it data, just random points in high dimensions. And now you're going to be looking at high dimensional spheres. So this SB is a D-dimensional hypersphere, and you're going to be generating random uniform points on these hyperspheres and seeing how they behave bizarrely, sort of like we saw with the unit cube example in Tuesday's lecture. Okay, so that's the homework number 1. Again, for this first section of the course, there's not really any machine learning involved yet, but just getting our minds around topology and manifolds at this point. Okay, questions? Yes.
So are we to expect typically for the homeworks that they'll cover like all sections prior to the homework being due? So like for this homework, we'll also need sections 2 and 3 in order to complete it?
In this, yeah, that's a great question. Usually we try to be, yeah, that's an excellent question. So everything you need for homework 1 is up to manifolds. You don't need Riemannian geometry. And this is typically what we'll do for homeworks, and not 100% always exactly this timing, but try to have everything you need for the homeworks. You'll be learning it as you're working on the homework, but you'll know everything you know with a few days, maybe a week or more to go, so that the last problems you have plenty of time to finish. Yeah.
Okay, thank you.
And yeah, so maybe to expand on that, you can do problems number 1 and 2 at the end of today's lecture if I stay on time. And definitely by the end of next Tuesday's lecture, problems number 1 and 2 are the topology section. And really mostly the first half of the topology section, we'll be able to do those. So yeah, so the goal is you'll always be able to get started as soon as you get the homeworks, and won't be waiting for us to teach you stuff. And then one more thing I guess to mention is I mentioned on Tuesday, Aman and I are going to alternate topic to topic. I'm taking the first topic, topology. Aman's going to do manifolds, and then I'm going to come back for Riemannian geometry's plan. We'll stick to this plan, assuming we don't have any extenuating circumstances and then we can always fill in for each other if we do, but yeah. Okay, I think that's all the logistics I had. Any other questions? Anyone on Zoom, feel free to speak up too if you have questions. Okay, then without further ado, let's talk about topology. I want to start out with a couple of visuals. So this used to be on the Wikipedia page for topology. They removed these little animations. I'm not sure why, but I dug them up. They're still on the Wikimedia. So this example. So first of all, what's topology? So intuitively, the kind of a popular way to think of topology is if I had a ball of clay and I was allowed to do the following. I'm allowed to stretch it, squish it, twist it, and warp it however you want, as long as I don't rip it and I don't poke any holes in it, okay? And I can't add extra pieces of clay. So I've got one kind of piece of clay that I can, this is an oversimplification of topology, but generally speaking, topology, all of those things would be the same topology if I do that with clay. Okay, so here's an example of a coffee mug is topologically equivalent to a solid donut torus, a solid interior of torus. So you see, if you imagine this made out of clay, I can take you know, a torus, I then can deform it like so. The handle's still there. I'm just pushing down the interior there to make an indentation for the coffee mug. So this is all things I can do in keeping the topology the same. The geometry of this object is changing, right? The geometry of a torus and the geometry of a mug are different, but the topology is the same. Anything I'm doing here is a topologically equivalent, something called a homeomorphism. Okay, so you can kind of keep this sort of intuition in your mind when we talk about topological spaces, is that we are going to think of the topological properties of a space are being invariant, or they don't depend on the exact geometry of the space. They don't depend on if I warped and smushed and squished the space around, but they do depend on the connectivity. So if I tear a hole in the space, I've changed the connectivity somehow, and that is a topological change, a difference in topology. And then another animation that used to be on Wikipedia, which I think is funny, is this cow deforming into a sphere. And so this cow toy, even though it has very interesting geometry, horns and ears and eyes and so forth and so on, legs, topologically it's just a sphere. You just blew it up like a balloon. Nothing's being torn or pulled apart or added to the picture here. It's just being stretched, if you will, and that's topologically equivalent. So this, we would say that this cow toy is homeomorphic, topologically equivalent to a sphere. Okay, so that's really what we're talking about when we talked about topology. We just keep those kind of that conceptually, this deforming clay example in your mind when we talk topology. And of course, we have to be more general than just these. These are really just objects in 3 dimensions. If you think it's a surface, it's a 2-dimensional thing. If it's solid interior, it's a 3-dimensional thing. But we're of course going to be thinking about where our data live. As we talked about on Tuesday, it's very high dimensional spaces. We can't really exactly bring this, our 3-dimensional intuition to those spaces, but some of these concepts, it helps to think intuitively about what things we're used to. Okay, so this is what we mean by topology. And let's see, I think that's everything I need on the screen. This is going to be on the board, the lecture. So I'm going to just turn all this off and go to the board. Sorry, it takes me a second to get to the correct. Okay. think I need to. Shoot. Oh, why does it stay? Oh, here we go. Turn on. Yeah, that's what I'm looking for. Oh. The off button for this one does not want to vibrate. Okay, cool. Okay, and now for the people on Zoom, hopefully the camera will follow me to whichever board I'm on, and if it doesn't, and I'm not aware of it, please unmute yourself and yell at me to fix the camera, because it might not always be easy to see what I'm doing. Okay. Right. Okay, so starting out maybe with a little bit more motivation about what is topology. And this is a little more mathematical motivation, but topology is really the study of continuity. So if you go back in your education, whenever you learn calculus, right, Calc 1, and you learned what is a continuous function. If you remember, you probably learned this epsilon delta definition of a continuous function from a real number to a real number. And if I find an open interval, if you give me any open interval epsilon in the output, that means there exists some delta with open interval in the input, such that it's completely contained. When I map it forward, it's completely contained in that output interval. This is the epsilon delta definition of a continuous function. And that continuous function definition, really just all it's relying on is as things, or the objects in that definition are open intervals. What's an open interval? This epsilon open interval and this delta open interval. Okay. We'll talk about continuity more on Tuesday, the more general definition of it for topological spaces. But the bottom line here is that to get to continuity of a function, you need to know how the function maps around open intervals. Okay, and so topology, in order to generalize what it means for things to be continuous, we need to generalize what it means to be an open interval. So we want to be able to talk about topological spaces that are more general than just the real line. And to do that, we need to generalize what we mean by open interval. Okay, so that's another way to think of, to motivate why we're doing topology. Okay, and so we'll start with just the definition of what it means to be a topology. So we're going to be given a set X, and X is really any set you want. Okay, it can be numbers, it can be just abstract points, it could be vectors, it could be really just about anything. It could be the people in this classroom are a set. We could put a topology on this set of us in the classroom. Just really abstractly, any set in the world, we can start with that set X. Okay, then a topology on X is a collection of subsets of X. And we're going to give that a letter typically in the notes. It's a script T for topology. So a topology on X is a collection called script T of subsets of X that satisfies three rules. Okay. Rule number one is that the null set is just, if I put curly braces with nothing in it, that means that it's a set containing nothing. The null set is always a subset of any set, right? So that's a subset of X. The null set and the full set X itself, which is also a subset of X, are both in the collection T. So remember, T is it's a set containing sets. So this is a set and this is a set that are both in the collection T. They're both in the topology. Okay. Number two, a union of arbitrary collection from T is also in T. So take any collection of these subsets in T, I take their union, that has to also be in T. Okay, and when I say arbitrary, I mean it could be finite or it could be infinite. If you're familiar with the different flavors of infinity, it could be countably infinite, uncountably infinite, it doesn't matter. It's any collection you can come up with of subsets that are in T. You take their union, it's also in T. And then the third rule is that or an intersection of a finite collection from D is in T. So intersections act differently from unions. I can't take any arbitrary sets out of T and take their union, or sorry, intersection, but I can take some finite number of subsets that are in T. I take their intersection and I get another subset that has to be in T. Okay, so these are the three rules for a topology to be, and sorry, I realized if I move over here, the camera shifts. Yeah, so these are the three rules for a topology to be defined on a set X. Okay, any questions about that? It's very abstract. So if it doesn't, it's like, okay, there's a bunch of rules. They don't make sense yet. That's okay. We're going to dive into making sense out of these rules here. But does everybody understand at least the definition? Do you have any questions about the definition at this point? Okay. Right. So let's checking the board is coming with me or the camera. Let's think about, oh yeah, first of all, let me make another definition, or just this is really just a terminology. Elements of a topology T are called open sets. Okay, and again, when I say element of T, it's of course a subset of X. And that are listed in T, those subsets are called the open sets. Okay, so one thing to point out is that not all subsets of X are necessarily in T. The ones that aren't in T are not open sets. The ones that are in T are called the open sets. So it's like we're labeling certain subsets of X to be called open. And again, the terminology open is not an accident. It's not, sorry for the word again. It's not a coincidence that is the same word we use for open intervals, because that's the type of thing we're trying to generalize when you talk about topology. Okay, really quickly, I'll give a couple examples of basic topologies we can make. So one, we have what's called the trivial topology. And this holds for any set X. I can make T be the null set and the full set X, and that's it. Okay. So any set I can define a topology called the trivial topology with just the null set and just the full set X as the open subsets. Everything else, any other subset of T is not going to be open. Okay, and you can check the three rules. The first rule is satisfied because the null set and X are in there. The second rule is satisfied. Any union of null and X just gives me X, or null in itself gives me null, and those are in there. And again, intersections are easy also because any intersections between null and X give me null, X and X gives me X. So any intersection of things in T is also in T. Okay, so that's an easy one. And it's one we can put on any set at all. Any set at all can be given a topology is the point. It's not a very useful topology. It's not good for very much. Another one that can be applied to any set in the world you want is what's called the discrete topology. The discrete topology just says that the set of all subsets that are open is all possible subsets of X. We denote this as very often as the power set 2 to the X is the notation. It doesn't mean a number 2 to the X. It just means the set of all possible subsets of X. I could write that as all sets A such that A is a subset of X. The collection of all sets A such that A is a subset of X. Okay. Again, it's very easy to check. Null and X are subsets of X. They're in there. Union, since everything's in there, the union of anything's in there. And since, again, everything's in there, the intersection of anything that's finite is also in there. Yeah.
The empty set necessarily a subset of X or any set?
Yes. If we say the definition of being a subset is, and it is kind of like this it's like a kind of like a logical thing you have to think carefully through. If we say the definition of being a subset is that every element of the set is in the, let me write it this way. If A being a subset of X means that if I give you any element of A, it's also an element of X. So this statement is vacuously true if A equals the null set, because any element of null is not there's nothing in null. So it's that you have an if-then statement, and the if part is always not able to be satisfied. So the then is always true, if that makes sense.
For the trivial topology, do you have to say that it's subsets of the null set and X, or could you just say X?
For the trivial topology, yeah, you always have to put the null in there.
Okay, if the null set is a subset of X, why do you have to put it there?
Well, so are you asking why do I have to put it like in the definition that the number one rule is that null has to be in the topology, or are you asking?
I guess I'm asking if there's a counter example.
Okay. Yeah, okay. Well, I see a counterexample, like if I didn't have that in the rule, that things would fall apart, let's say. That's a good question. What falls apart in topology if I remove, like if I said topology, if I come back over here and just said, yeah, the topology rules are this, right? Just get rid of null being required to be in the space of, in the set of open sets. That's a good question. I'd have to think about what, we haven't talked about really what these rules give you other than a definition so far.
We don't have to burn time on it.
Yeah, no, I appreciate that. It's an excellent question. I have to think about. I'm sure a counterexample where something breaks down if I don't have that in there. But it's so because yeah, if I take that out, then the three rules are logically consistent. You could have those as the three rules with the null removed. And so yeah, it's a good question. What falls apart in the theory of topology I'm guessing the definition of continuity breaks, but I'd have to think about why. So maybe on Tuesday I'd have a better answer for you if I think about it a little bit. But yeah, it's a good question. Okay. Excuse me. Okay, so these are two examples of topologies for any set. And again, they're not super interesting typically because you can put them on any set. They don't have very interesting properties, especially the trivial topology. The discrete topology, notice that every point in your set is already an open set itself. Because a 1-point set is a subset, and so even just a single point is an open set by itself. This is really why it's called a discrete topology, because every point, in some sense, has a little neighborhood, a little open set all to itself. So the points are somehow separated. So one thing about topology is this notion of separability. And we could say I can put a point in an open set by itself. It's separable from the rest of the set X in that topology. And so that's why we call this a discrete topology. Okay. I think the next thing I like to do is give, just some very, very basic, simple examples of topologies on a 3-point set. So if my X were just 3 points, and I'll just label these points A, B, C, but this is just not a concrete set of points. It's just any 3 points. I'm going to call this my set X. So let me write that as X is the set A, B, C. Notice the trivial topology is, and I'm going to draw open sets as just kind of circles or just circling things. So the trivial topology, and of course I can't circle the null set there because it's nothing. So that's always in the background. It's there. But yeah, the trivial topology is just this picture that the only open set of the null set is all of that. Okay. The discrete topology on this picture, and I'll stop writing the letters A, B, C just for sake of cleanliness of the picture, is again, every individual point is an open set, and then any combination of things I can get, the 2 element sets are all open sets, and so I gotta get A and C is the 2 set there. So basically any kind of collection of points I can circle gives me the discrete topology. Those are the open sets. Okay, but then there's actually several more topologies I can put on this ABC set, and the point of this exercise is just to get you to mentally go through confirming the 3 rules hold or don't hold, and also to kind of make the point that even for a very simple set, just ABC here, there's not just a unique topology. The topology is like an extra structure I'm adding on top of a set, and I could do that in multiple different ways. So I've got 2 different ways. These are 2 different topological spaces, even though the underlying set X is the same. Okay, so let's do a couple more examples. Let me just do the following, and I'll ask the audience, ask you out there, is this a valid topology? Null sets included, and now I've got just the full set X, and then a subset AB as in the topology as open sets and nothing more. Is that a valid topology? And you can blurt it out or raise your hand, one or the other side. Okay, yeah.
I think it is a valid point.
Okay, great. Yes, that is correct. This is a valid topology. If we look at unions, the only thing I can really do is the union of X in this subset AB, and the union there is all of X still. There's not really any other interesting combinations, so the null set doesn't really do that much. Intersections, again, this works. So if I take the intersection of this and the X, I get again AB, and we're good to go. Okay, yeah.
Just,
Uh-huh.
but anyway, so basically when you talk about the collection, it explicitly means the open sets within the topology.
Yeah, when we say a collection from T, that means a collection of open sets. If I select some number of open sets out of the topology and then do a union with those or do an intersection with those, that's what we mean by collection.
Okay, so in that case, our topology is just empty set AB and set ABC, right?
That's right. Yep. Mhm. Yeah, so let's write that. So here T is null. It's all of X. That's always going to be in any topology. And then there's one additional one, which is the set A, B, like so. So that's the way to write that topology. And so notice, sort of again from Zoomers, the board flipped on me. So notice that T is a set of sets. Let's always try to keep that in mind. So I've got kind of curly braces of the set AB, that's the open set, but T is another set of curly braces outside, which is saying that each element of T is itself a set in X. T is not a subset of X, right? Because its elements are not elements of X, its elements are subsets of X. So you gotta have kind of this set of sets thing in mind. Okay. Let's do, yeah, good, go ahead.
Sir, could you give me an example for the invalid topology? Invalid.
Say again, the what topology?
Invalid.
Oh, invalid. Yeah, that's great question, because that's exactly what I was getting ready to do. Let's do okay. Somehow given away the game because I was going to ask you if it's valid, but now that I'm telling you it's not going to be valid. So let's try to come up with one that's actually, I'll ask in the following way. How can I make this invalid? Can anybody tell me, let's add one more subset here to make this not a topology. So start with this thing that is a topology. Let's add one more subset. Can anybody think of how would I add one more subset and then break just one more subset, no more, and then break one of these rules? Yeah, back there.
Add a disjoint set Y.
Say again, the set.
Add a disjoint set Y into the T.
So by circling, you want to circle this dot here, is that?
Like outside the circle, any
Oh, no, but let's make it that I have to, yeah, okay, without adding another set. I should stipulate, you're right, you could do it, yeah, I could do that, adding another set. But let's do it by circling and getting another subset of the 3 points. That is a valid way to do it, yes.
Add B and C.
Okay, yep, and so the B and C would be these 2 points. And then maybe someone else tell me, why is that not a valid topology? Yeah, back.
Section breaks.
Yeah, the intersection breaks because I'm missing the intersection between these 2 is B. I would need that to be in the topology for that whole thing to be a topology. Now, if I do add that, do I have a topology? I add that one extra subset of B. Now I've satisfied all of these. Yes, that's right, I have. So I've got union in there, any intersections, the intersection B with anything is B, and I'm good to go. Okay. Yeah, so you can keep going with this example, and I encourage you to do that if you want to get more of a sense of these rules, intersection union rules. Try a few more of these. As you can imagine, there's quite a lot of different combinations of sets of subsets of this simple 3-point set. And of course, you could do it with different permutations of the letters A, B, C, but that's not as interesting. But even without doing the permuting, you get quite a few different topologies here. Okay. All right, any questions on that example? That's kind of just to start to get a sense of what these rules are doing. All right. Before we do any more examples, I'm going to do one more definition that helps us build topologies from sort of building blocks that make it a little bit easier to define topologies. And this definition is something called a basis. So a basis for a topology And it's usually denoted, a basis will be denoted with, again, script B here. For a topology. And I mentioned this in the notes, but really a topology, you should specify a pair X, the set, and T, the space, the set of open subsets. But I'll usually have an abusive notation, just say X when the topology is well understood. We know what topology we're working with. Or here I'm just going to use T and leave out the X. The X is in there and behind the scenes there. So yeah, so a basis B for a topology is a collection of subsets of X such that the following holds. And okay, I need to be careful. Yeah, I don't want to specify what the T is here. So just for a topology, we'll see how it generates the topology in a minute, but just a basis B for a topology is going to be a collection of subsets of X such that the following holds. If I have basically, yeah, I need two rules for every point in my set. There exists a basis element that covers it. So there it exists and you have to be careful with my handwriting here. Just a normal B is an element of script B. So again, B being is just like the script T is a collection of subsets of X. Script B is a collection of subsets of X. So B is a subset of X. So just a note here, this means that B is got to be a subset of X. So this is a set. So for every point in X, there's a basis element, capital B, such that this point is in the basis element. Okay. Another less roundabout way, maybe of saying this more matter of factly, is that you've got a set X, and the basis elements have to cover the whole set. Okay, so if I just laid all the basis elements on top of my set, every point's covered somehow. Is what this really means. Okay, and then number two, if you have two elements, basis elements B1 and B2, have a non-empty intersection. If B1, B2 satisfy B1 intersect B2 is not empty. So there's something in the intersection that they overlap somewhere. Then there exists and this means there exists, if you haven't seen that before, there exists a third basis element such that B3 is contained in that intersection. Okay. And so this, I think it helps to have a picture, kind of like Venn diagrams, if you will. What this means is that if I have two sets, these basis elements B1, B2, they overlap, their intersection's non-empty. It means that I can find a third basis element, B3, which is fully contained in that intersection. Okay. So these again seem sort of like esoteric, abstract rules that we've made up seemingly out of nowhere. But this is what's called a basis. And I erased the T here because there's no mention of the T here. I realized that I needed to say not of a specific topology quite yet. So you might ask, what does this have to do with the topology rule that we made over there on the far left board? What we're gonna see is that instead of defining open sets directly, I can instead define these basis sets and then use these basis sets to then automatically generate the rest of the open sets in our topology. So these basis sets, B will be sort of the generators of the open sets. They themselves are open sets, but they're going to then generate the rest of the open sets in our topology as well. Okay, but any questions about, yeah,
You say the B's themselves are open sets, right? So shall we specify them because you just mentioned that subset of X and X itself isn't topology, therefore X make an like subset point C will be a subset of X, but it's not gonna be an element of topology. So, and if we somehow like put C in the basis and be like, okay, that's not an open set, then B is not open. Like, is specification important in the specification? So from the rule, it will always be the case, and B will be an open set.
well, so let me explain how we're going to generate. Yeah, let me explain how we're going to generate the open sets from the B's. And then I think that'll answer your question or your comment. Yeah. Yeah, so let's do that. So, and if it doesn't, the board was not. Okay, I apologize to everyone on Zoom again. I don't know how long the board was misaligned with where I was, but hopefully you saw the definition here. But any other questions on the definition for, we're going to hopefully clarify this, how this relates to topology and open sets here. Yeah.
Is the small x singular elements of X or is it also a subset of X?
Oh, this here. Yeah, good question. This, yeah, sorry, I'm being a little bit ambiguous with my subset notation. I don't really distinguish between this notation and this notation. It's a little bit ambiguous. This does not mean strictly less than, if you will. So maybe let me be consistent and do this. What this means is that B3 is a subset of this intersection set. It could be equal to this set. That's okay. It doesn't have to be strictly less than, like there's an element it's missing necessarily. Yeah, that's a great clarification to make. Whenever I say subset, I'll try to stick to this version of it. It means it could be equal unless I say otherwise. Yeah. Yeah, question?
So then what's your symbol for saying that it can't be equal?
Yeah, I mean, I don't think we need it. So fortunately, but yeah, I guess I mean, some people do use this to mean a strict sort of subset, meaning less than. But we don't really need it that I can think of in our topology discussion as far as I can remember. Yeah. Okay. Great. So then let's then make the connection from basis to topology. And it's fairly easy. So the topology T generated by a basis B is the collection of all subsets of X that are unions of elements in B. And I really could, again, throw in the word arbitrary to be arbitrary unions of elements in B, meaning you can take an infinite number of of these sets in B. It could be finite or infinite, doesn't matter, and union them together. You can also take an empty collection of elements of B, and then your union is going to be the empty set. So you get the empty set of there. That's one of the things we need, right? So this is when we say we're going to generate a topology from a basis. We don't have to define, list every single possible open set. We can just list a basis set and then generate more open sets through this generative process. Notice also when I said the elements of B are open sets, that follows from this definition of generating, because I can just select one element of B and its union with itself is just itself. And so that any element in basis element is an open set itself. Okay. Just to give some examples, again, really quickly. This is kind of the trivial topology. The basis is just X, and I get the trivial topology because the only thing I can get with unions of X is just X, and the null set again, I said it always comes along there. The discrete topology we did. I actually can write it. Well, no, I can't actually. It's the set of all individual points, 1 point sets such that X is the point in X. So if I say every point in X is an open set for a basis element itself, then all possible unions are going to give me again the power set. All subsets of X are unions of 1 point sets in X. So this would generate the trivial topology. Okay. Any questions about those two simple examples? You might, again, if you're working through that ABC 3-point set, think about various combinations of subsets as being basis elements, and then see what you can generate as unions of those things and see what topologies you get. One thing that I'm not doing here, which would be necessary if we were in a rigorous math class, is proving, right? Because I just made the statement, this is how you generate a topology, but I didn't prove that the thing you get in the end is a topology, right? So I'm going to skip that kind of proof. It's fairly straightforward to do it. If you want to think more deeply about these, convince yourself that that if I do this process, I take any collection that satisfies these two rules, and then I take any unions of those things, that I will then, the resulting subsets will satisfy these three rules. Okay, and then that proves that a basis, when you go through this generating thing, gives you a valid topology. Okay, so why am I bringing up the basis? This is to get to sort of the goal here is to get just the basic foundation, what is topology, and to bring it to what you do know, which is the real line and its usual topology, and also Euclidean space, so d-dimensional Euclidean space, vector space, and its usual topology. And we usually think of the real line and Euclidean space through the lens of the basis that defines their topology. And so let's go through that example that maybe will give us a good intuition for what these definitions are trying to do. So let's take the real line first, just a set of all real numbers. Yeah, question.
Quick question, just to double check, did you say the first example basis that generates the trivial topology, and then the second example basis would generate the discrete topology?
That's correct.
Okay,
Yep.
thank you.
So the real line, we're all familiar with, all real numbers. By the way, I could give it the trivial topology. I can define the basis, the only basis element to be the whole real line itself, and then I get null and the real line. Is the trivial topology, again, not the topology we typically use for the real line. Or I could give it the discrete topology. And of course, we kind of, since our early childhood ventures into mathematics, think of the real line is continuous and not discrete. Things like integers are discrete, the real line is continuous, but that's because of the topology we put on it, technically. You could have a discrete real line. The real line can be discrete if you give it the discrete topology. Okay, so I give it the basis element that every real number is an open set itself, is a basis element, and then any subset of real numbers is an open set. And that would be a discrete topology, which is not, again, how we usually think of the real line being continuous. So the way we usually think of the real line is with the following basis. And that's very simply the space of open intervals. And I'll just write it as follows. So if I'd say, and A, B are real numbers, and in the order A is the smaller of the two, then all possible open intervals is the basis we put on the real line. And if I think of then what is the topology for the real line under this basis, it's any possible union of open intervals. Okay. Now, if I take two intervals that overlap and I take their union, I get a bigger interval, open interval, but I can also get two intervals that don't overlap and take their union and get collections of little open interval segments. And there could be an infinite number of those. That would still be an open set. But all your open sets in the real line are going to look like some collection of varying length, possibly open intervals. Okay, and this is the topology that we think of when we think of the real line and continuous functions, which we'll dig into more on Tuesday, what continuous actually means. Okay, then we can extend this to higher dimensions. So if I say RD, meaning d-dimensional vectors with real entries, real number entries. Now we can take this exact same concept of a basis of open intervals and extend it to open balls in the vector space. And this is going to look like the following. I will define length notation here in a second. VXR is going to be an open ball centered at X with a particular radius R. I'll write that explicitly in a second. So X is just any point in, whoops, X is RD, sorry. Any point in RD, and R is a real number greater than 0. So yeah, so to be clear about what VXR means, it's a subset of RD, which is all Y, Y in RD, I should say, such that the L2 distance or the Euclidean norm between X and Y is less than the radius R. Okay, and just to draw a picture, what this means is, think here R2 is the blackboard, right? I'm at some point X, and then the ball about X, where the radius of that ball is R. I'm shading in all points inside that radius up to, but not including the boundary. The boundary is, that's why it's a dashed line, is that that's an open ball, not including the sphere, or in this case, circle, that's on the boundary. It's not included here because I have a strictly less than. Okay. So now in higher dimensions, this open set concept gets a little more interesting here. You know, you just got little interval, open intervals kind of strung along the line. Here, okay, so here, I can take any number and it can be infinite, arbitrary number of these open balls and start unioning them together. And so if you think about just mentally, what can I kind of put together when I do this process, I can really get any kind of region with any kind of shape you want it to have. As long as the boundary of that region is open, in other words, not included in the set. So any kind of open boundary region is an open set. And of course, they don't have to be, it doesn't have to be one connected region. I can have, multiple, and again, I should dash these lines here, but I can have multiple of these regions disconnected, but all kind of union together into one open set. Okay. I should mention that the way I'm drawing this, the boundary looks nice and smooth and round and everything. That doesn't have to be the case, actually. You can have sharp edges and corners in the boundary here. If you think the limit, as I add smaller and smaller balls, I can get a sharp point. So the smoothness, which gets into differentiability derivatives, is not a property that it's just the way I drew this, but the openness of the boundary is an important key property here for this to be an open set. The boundary can't really be included. There's a hard boundary. Okay. Any questions there? So topology, now we've gotten the definition down and the basis, how you generate it, leads us to the space that we're most familiar with in our lives, probably the real line and the multivariate version of it, Euclidean space, vector space. What we get is that open sets really just mean kind of the open regions that you can draw in Euclidean space. And that notion of an open region is what gives us the topological structure of RD. Okay. Now, what is that topological structure good for? We will see on Tuesday, but it lets us define what it means that when I map from one Euclidean space to another Euclidean space, that map is continuous. Okay. Any questions about that definition? Okay. I'm going to then for a few more things out there in the last 10 or so minutes we have. So we got the concept of an open set, and we can also define something called a closed set. And let's just assume I have a topology T again. A closed set is the complement of an open set. And by complement, I mean set complement. So let's say I've got U is an open set, meaning it's an element of our topology that we're currently thinking about, whatever that may be. We've got an open set in our topology. Then if I take X, and there's lots of different notations, right, for complement, but I'm going to say X minus U. That is closed, or a closed set. And just to be kind of super crystal clear, X minus U is all points Y, such that Y is, it's all points Y in our set X, such that Y is not an element of U, right? It's the complement, the set complement within X. Okay? One thing you can show very quickly is, again, going back to real line, and this notion of open sets that we have is just unions of open intervals. Then we can get the closed sets. It's fairly easy to see the closed sets are really just unions of closed intervals. And now a closed interval could include the two endpoints being equal, A and B being equal, and so that's just a single point. That's also a closed set. So single point is a closed set here. But what is the U that would give me a single closed interval? Well, minus infinity to A, and then B to infinity, positive infinity, are two open intervals, because I can keep going off to infinity for my open intervals here. And the complement of those is the closed interval AB. So AB closed interval, convert relationship right off this notation. A B is a closed set under this usual topology in the real line here. Okay. One thing to point out is that if I give you a set, there's a topologist joke, which is that sets are not like doors. They can be neither open nor closed. They can also be open and closed at the same time. So if you think about the null set and X, let me put bracket around. They're complements of each other. They're both open sets. So the fact that they're complements of open sets means they're also closed sets. So null and X always in any topology are both open and closed at the same time. So open and closed are not really opposites of each other, even though we have doors, right? Open and closed, you can't be both. But yeah, they are complementary, but that doesn't mean opposite. The other thing to point out is, I can have a set which is both open. Sorry, this is both open and closed, but I can have sets that are neither open nor closed. So for example, again, just in the real line, if you take the set A closed and then the other end open, this is neither an open set nor a closed set. Okay, and it's even easier to see if you go back to those ABC examples, some of those sets. If you go to some of those examples and think about them, you can get some topologies where some sets in there are neither open nor closed. You should think about that carefully. Yeah.
Are we able to use the example of the ABC from earlier to define what a closed set could be? Or is that not present?
You can, I mean, so the ABCs for a specific example, you can define, and sorry, I'm using AB here as a different the context. AB here, the notation means points on the real line. ABC before were just labels for 3 points, just to be clear there. But yeah, you can do examples of closed sets for that set X, that ABC set, but it doesn't expand to the other possibilities like the real line. Let's do one example really quickly. I mean, just to, so we had ABC, and this is here everything is the X and null are both open and closed in the trivial topology. But notice that if I took, and I'll put the labels back on ABC, if I took just one subset of a single point, because this is still a valid set, it's just that it's not in the topology. It doesn't have to be in the, so notice the closed sets are not in the topology typically either, unless they're also open. But here, let's say the singleton set A, it's not open and it's not closed, right? Because its complement is BC, that's not an open set, so it's not closed. So here's an example of a set in this topology that's neither open nor closed. Okay. Yeah, any other questions about sort of these basics? And so, yeah, so a lot of topology is very much, just abstract, verifying rules are satisfied and things like that. But if we bring it back to spaces where we're very familiar, like the real line or Euclidean, deep dimensional Euclidean space, We started to see where these definitions came from and sort of what they mean. And when we talk about continuity, and this concept of topological equivalence, we'll see again more about why we wanted to define things this way. Yeah.
Could you just repeat the reasoning again as to why the set of A is neither open nor closed?
Yeah, so under the trivial topology, which, yeah, now we'll put curly braces here. This is the trivial topology of these are the only open sets is null and X. And so A is not in our topology, meaning it's not open. Okay.
Okay.
And then it's also the case that X minus this, the complement, which we know is the set BC, this is also not an open set. And therefore, if A is not a complement of an open set, it's not a closed set. So it's neither open nor closed. Mhm.
But it's only for the trivial set or trivial.
For the trivial topology in this example, that's right, yeah. Mhm. Now, I could also do one of the other topologies we have. Like say this one we said was a valid topology, and again, A is not in the open sets and it's not a complement of an open set. In fact, then if I did, let's say I did this one. We had this one was our last like valid topology we did. Now, what do you think? Is A open, closed, or neither, or both? I guess there's 4 options. Yeah,
It's closed.
that's right. A is closed because now we do have BC and that's open. Complement is closed. That's right. Okay, so yeah, you can keep playing these games. We're out of time. I encourage more right on the kind of sketching out all of these topologies or not topologies, open and closed sets on the ABC example. Get a sense and play it with some basis combinations on the ABC set and get a sense for how these rules all work. All right, thanks.